Hey everybody, welcome back to Calc 3 Online. So the plan for today is to talk about surface area and doing this with double integrals. And you can kind of almost see where this comes from if you just actually go back to arc length. So if you take some sort of like curve or something, and you compute like, say, the arc length from like A to B, right? This arc length right here can actually be arc length. So this arc length could honestly be understood as like a 1D surface area just for that curve, right? And so if we think about how we found that before, we did that with the integral of the square root 1 plus dy dx, that's a y, all the dy dx squared dx. That's how we did arc length, and then it would be like A to B for this problem. And so it's pretty reasonable to take that and kind of guess that where we're going with double integrals, if we truly want to do like the 2D surface area of some surface, then it's pretty reasonable to think that we would have a square root 1 plus the partial of x of f squared plus the partial of f with respect to y squared, and then like a dx dy, maybe even just more in general, like a dA, some area element. And this really is the true like 2D surface area, but I wanted to show where that comes from a little bit more too. So just to kind of sell you on why this actually works, not just to make the connection between these two, but there is a connection between these two. All right. So surface area, we're just going to build up, honestly, this formula right here. And the idea here is you've got like your surface in blue, and we have like this red tangent plane, okay? And that red tangent plane is being called just like delta t sub ij, and it just, it's like an arbitrary tangent plane based on what arbitrary region you're over kind of here. So that is just the idea, like that this covers some sort of smaller patch of S in there, the smaller patch of S being delta S sub ij. And so therefore, if you basically just do a double sum over all of the t sub ij's, right, then that would be a good approximation for the total surface area, right? Basically we're just going to have like, another like red square here and another red square here and another red square here. And so we just cover the surface S with a bunch of these tangent planes. That's the idea. I get rid of that because I don't want to make it too crowded. And this approximation would improve, right, as the amount of rectangles increase. Right? So basically we need to let these rectangles down here get more and more and more of them, right? And so, the idea is like if you kind of imagine splitting that into 4 chunks, right, then the little corresponding tangent plane up here can be better, right? And so you would get a better approximation. So that's like the idea with this. So if we want to let the amount of rectangles increase, then that's kind of implying that we're going to need some sort of limit, right? So the surface area is going to be a limit. I'm going to use m and n and let those go to infinity. And we're going to sum from I equals 1 to m for one of them, and then j is going to go from 1 to n, right? And this is going to sum on all these t I sub j's. So, basically just saying we're splitting x up into n subintervals, and then I is like an arbitrary 1 in there, and then we're splitting y up into m sub, no, I had that the other way. M is x, and n is y. But the point is, basically, sum over all the little squares here, all the little squares here, make them really, really small. And if you do that, you get a really good approximation. And so we should get a good surface area, basically. So the question becomes, how do we find this t thing then? So t can be just thought of as like the span of two vectors, like a and b, all right? And if we just kind of go back to some chapter 12 stuff, right? We know that if we take the magnitude of the cross product of these two vectors, then we truly get the, the area of t. That is just like an important result from chapter 12. So if we now know how to find t, then the question becomes, how do we find a and b? And so that's what I'm going to do on this slide. So to find a and b, this is probably like the trickiest little part here. So what I'm going to try to show is you can think of this. So you want to kind of look at this. I'm viewing it as like it's kind of going, as we come towards this corner, we're going down, like the surface, based on here, it's like it's curving down, right? And so, so we're going to go downhill this way. So you can think of a triangle here where it's like you go over this vector, and then you're going to have to drop down, and you could sort of create this triangle, right? And so this vector A could be thought of as this vector, and then plus this vector, right? That's like, then A would be the resultant of those two. So boom plus boom, like this plus this would equal A, right? And likewise, we could do, we can go over in, I'm going to try to draw these a little better because I should be, there we go. I think that's a little better. So that's one vector. And then I'm going to come down another vector, and then that will form this triangle over here. And then I'm going to go over some amount there on the same level as this point P. And then I'm going to drop down again to get to that corner right there. So that I'll have a triangle there, and I'll have a triangle there. And so based on this, right, this yellow part right here, so I'm just going to try to color code all this, is just truly parallel to the vector delta x. So to get A, I'm going to do delta x in the I component, right? And that's it, because it's just parallel. Then I'm going to add to it, I have to drop down some amount, and the amount would be basically the same as the slope change, right, of this thing. And actually, it'll be the same thing over here too. So, the slope change is just going to be like f sub x, because it's in the x direction, evaluated at whatever x sub I, y sub j is, right? This is like my slope change. And then scaled by delta x, because that's how much I'm moving. And then it's going down, so I need that in the k direction. And so if you add yellow plus purple, you will get red. And likewise, if I do this one, all right, B would be like delta y in the j direction, right? That's the blue part. And then the green part would be like the slope change. Now it's like a partial in y, right? Evaluated at the point. So this is my slope change. And then scaled by delta y. And that's the vertical component, delta, or k hat, right? And so then, if I just do a cross product, okay, I would get, let's see, I'm just going to get this. And here I'm saving myself a little bit of time by just not putting in the, this is like a number, f sub x and f sub y, just evaluate it at that point. So then, if you just go and compute the cross product, you would get this. And so you can see, basically this is my cross product here, and then I had a delta x, delta y, and everything. So I took that out, right? And then I would be left with negative f with respect to x, f with respect to y. That's a negative. It's hard to see, but there's like a little space in there. And then this one, truly, you just take delta x, delta y out, so you have a 1. And so if you do the magnitude of this thing, okay, then you basically get if you just take, I think I'm going to put this down here. So if you just, do magnitude, which is square root of all these different things squared, you're going to get f with respect to x squared, f with respect to y squared, plus 1, and then you'd have like a delta x, a delta y. And this is where you're going to get this delta a, basically. And so that is what I'm getting, for this part, my magnitude of a cross b, okay? And so we can finally kind of go here, right? And so we now know that if we, once we bring in a limit to a problem, and we let these basically distances between n and m go to, we have an infinite amount of subdivisions, basically, then all my little deltas in here become d's. That's what happens, right? So this becomes truly a double integral of f with respect to x squared plus f with respect to y squared plus 1, and then dA. And that's it. And that is actually what we sort of intuitively said we should get over here, right? And this really does represent the surface area, just like arc length really represents surface area. It's just like a 1D version of surface area. So I just want to do one example, basically where we do this thing now. So I want to find the surface area of this x squared plus 2y thing, which is right here, that lies above this triangular region, T, in the xy plane, and it has vertices 0, 0, 1, 0, and 1, 1 out here, okay? So if you have all those vertices, I would personally start by just thinking about what they look like in 2D. Seems much easier. So here's 1, so that's 1. So that is my region I'm integrating over, okay? And so no reason to worry about polar or anything like that. You can just go ahead and do this with rectangular. So I'm going to go ahead and set this thing up. Basically, we can do this if we do it with we'll do dy dx, right? So we go vertical first, dy, so we go from 0 up to y equals x, and then we're going to go left and right, so we go from 0 over to 1, so 0, 1. And then we'll go and plug in the inside of this stuff. So we have the partial of this thing with respect to x is 2x, right? So we have 2x squared. Then we have partial of that thing with respect to y, which is 2. So 2 squared and then plus 1, which probably should simplify just a little bit here. So we're going to go ahead and get 0, 1. 0x, square root 4x squared plus 4 plus 1, which is 5, and then dy dx. And so it's a it's like a nice dy integral, right? Because you just literally tack on a y. So I'm going to do that one, and I would just get y times the square root of 4x squared plus 5 dx, and y is running from 0 to x. So we would just get 0, 1, x square root 4x squared plus 5 dx. And then just kind of another classic u sub problem. If we do u is 4x squared plus 5, du is going to be 8x dx, right? And so we have an x dx, right? So you would need to move the 8 over, okay? And so we could really just solve this thing by doing an integral 1/8, I guess, the integral square root of u du, which is just going to work out to be so let's see. So we got 1/8, and then we would have like u to the half there, so we got to raise that to 3/2, and then divide by 3/2 or multiply by 2/3. So we've got u to the 3/2, and we're gonna substitute here the u equals 4x squared plus 5. And so running out of room really quickly here. Basically, I'm gonna have a 12th, because I'll have 2 over 8, leaving me with a 4th, times 3 is a 12th, and then it's times 4x squared plus 5, all raised to the 3/2, and then you gotta plug in the bound 0 to 1, and I'm just gonna write what you should get, because I worked it out. It's just a weird, messy number. It's 1/12 times 27 minus 5 square root of 5. And that's it. So that is the surface area of this thing above that triangular region T, which you can see a little bit better over here. This thing is T. But that's it. Really, a lot of the problems with surface area are not meant to be like super tricky. They're more, I wanted to talk about how we arrive at this sort of formula for surface area.